Hi guys, this is Mr. Bishop. Welcome to our next screencast in Chapter 4. So we're going to pick up right where we left off the other day with our factors that affect future population growth graphic organizer. Let's take into consideration the population game activity that we did last week in class as we go through these slides. Think about how our deer population behaved when the environment resources were limited, and right with that we'll go to our next slide, which is environment limits the population size. So population of a species may change based on environmental resources. So in our population game we had food, water, shelter. These were all factors in our environment that limited our population size of deer. Environment limits population size continued. So environment can be divided into two parts, biotic environment and abiotic environment, and living and non-living parts of the environment affect population size. So again, this might be a little bit of restating some stuff, but that's okay. The food was our biotic part of the environment, and our shelter and water were the abiotic part of our environment, and they both limited the population size of deer. Limiting factors. An environmental factor such as food, temperature, water, or sunlight that restricts the type of organisms and population numbers that an environment can support. So we've talked about limiting factors before. We discussed them during our population game. Again, not to be redundant, but our population of deer, the limiting factors of our environment were food, shelter, and water. So we all remember that those were the limiting factors of our deer population. So again, even more environmental factors exist in true nature. Our population game activity was, a simulation of a deer population over many years, and in actual nature, in reality, we have to also consider temperature, sunlight, in addition to food and shelter and water. Density-dependent factors. So a density-dependent factor is a population increases, the effect of the factor increases also. Disease, competition. So density-dependent factors are typically abiotic in nature, such as food. So the more of a species that exists, the less food there is. The more one species, two individuals of the same species are going to compete for that food. Disease, again, large populations, there is more vectors for disease to spread amongst that population when the population is really large. So, for example, our population here in San Diego is quite large, and you can, every year, either during flu or cold season, the cold or flu can spread really quickly in a large population of San Diego because there are lots and lots of vectors, and by vectors I mean people. So people spread disease. It's just what we do. We are bacteria carriers. So that's why it is important to wash our hands and sneeze into a tissue and cover our mouths when we cough. And otherwise, we are vectors of disease. Bacteria can spread from person to person when we are sick, and that is how disease spreads. So it is also while conversely, if you're out in a more remote location, there are less people around. There's less exposure per person to other individuals who may or may not carry disease. So those people might be less likely to get disease or spread disease. Moving right along, density independent factors are usually abiotic factors. So temperature, storms, floods, droughts, these all affect the population of species regardless of how many individuals exist in that species. They're going to happen whether we like it or not. It's going to get hot, it's going to get cold, it's going to rain a lot, it's not going to rain a lot. The earthquakes are going to happen, hurricanes, tornadoes, fires. Although sometimes fires are started by people, but there are wildfires. All these events are going to occur regardless of the size of the population. Carrying capacity. So carrying capacity, again, we talked about this with our population game, is reached when a population gets high enough to begin destroying its environment due to lack of food or resources. So we noticed the other day during our population game that when our populations got up to 16, 17, 18, 19 people of deer, there are only 3 or 4 or 5 resources available in our habitat. So only 4 or 5 deer maximum could survive in our habitat, and that was only if the deer had selected to choose the resource that the 5 resources were available. So if a deer elected to go for water and there was no water available during our round of tag, then that deer was going to die. So the carrying capacity of that habitat for that round of tag was very limited because of the large population size, and there were only so many resources available to keep so many deer alive. And that is true in nature as well. Once our population gets really, really large, there are only so many natural resources available to support the population. Carrying capacity continued. If the carrying capacity is exceeded, a population will begin to decrease rapidly due to mortality and emigration. So mortality is death, and emigration is when individuals leave a population. So we can see right here towards the top of our graph, we can see that we have a carrying capacity up here about 1.5 million in this graph, and we can see that our population change has overshot that carrying capacity, and then it begins to fluctuate up and down around that carrying capacity for years and years. So carrying capacity, number, J-shaped curve, so exponential growth. K is our carrying capacity, and S-shaped curve is logistic growth. So exponential growth is population growth that goes on and on and on forever. So they just get bigger, the populations get bigger and bigger, and they exceed the carrying capacity of their habitat. Where an S-shaped curve, once the population reaches that carrying capacity, it tends to stay right around that carrying capacity. So there are 2 life history patterns. There are K strategists. K strategists have long lifespan, large body size, reproduce slowly, have few young, so they have 1 or 2 offspring at a time, and they provide parental care. So examples are humans, elephants, giraffes, we can see over here, are all K strategists. So they live for a really long time. They're usually larger organisms, that it takes long reproductive cycles. So, humans carry babies for 9 months. Elephants carry babies for, I think, close to a year. It takes a long time for the young individuals of that species to develop within the mother, and then there's parental care. Humans take care of their children for nearly 20 years to support them, and then they are old enough to support themselves, and those are K strategists. And then there are R strategists again. So an R strategist has a short lifespan, small body size, reproduce rapidly, have many young, little parental care. Example, cockroaches, weeds, bacteria. So these are organisms that survive by reproducing massive amounts of populations. So think bugs, think bacteria, think basically pests. You could think of like that animal organisms that humans consider pests. We don't like flies or roaches or rats or mice. So human population growth, as we saw in the video, we have the year 1000 down here, and we can see that the human population in billions of people were under 500 million people in the year 1000. We're very steadily growing for the years 100, 1100, 1200, 1300. The Black Plague occurs around 1400. A lot of people die. The human population dips. 1600, the population gets back up as people who survive the plague, people develop immune responses to the plague. We fix our cleanliness habits to survive the plague. 1800, the Industrial Revolution begins. We get electricity, agriculture. Suddenly, our food source availability is abundant, and the population hits an exponential growth. Major scientific and medical advances. People are living longer, healthier lives. And year 2000, we're over, 1 billion people and growing and growing and growing. So, again, carrying capacity, you can see a slow growth rate down here. So this is the slow growth stage of an S growth. Then there is a fast growth stage of an S growth. And then once it reaches carrying capacity, it goes back to a slow growth stage. Growth rate fluctuations. These normal ups and downs are called fluctuations. Fluctuations are caused by variables in the environment such as climate, food supply, disease, activities, and natural enemies. And growth rate fluctuations continued. If a population had unlimited food and space, it would grow at a certain rate, but factors in the environment affect the growth rate. J curve versus an S curve. So an exponential, that is our J curve. An S curve is our logistic growth. Let's remember both these terms. And we are around 14 minutes, so I'm going to wrap things up here. I just would like you to go back through these slides real quick, listen to the video, identify any areas you have questions about, any concerns you might have, and let's bring those tomorrow to discuss a little bit. We're going to continue on our journal articles, and we should consider, our population growth rates, J curve, S curve. Maybe in our articles we'll identify whether we have R strategists or K strategists, whether we think populations are going to grow on the J curve or the S curve based off the findings of our article, and these are all things we want to consider during our activity. I hope you have a good evening, and I will see you all tomorrow. Thank you.